inverse functions, how to graph them, and how to find them. If we have a set of ordered pairs, we know that's a relation. We can find the inverse relation by simply interchanging the x and the y coordinates. So let's consider the relation, the set of ordered pairs, and let's graph the current points in blue. So I have 2, 4, -1, 3, and -2, 0. And now we'll graph the inverse by interchanging and graphing them in red. 2, 4 becomes 4, 2. -1, 3 becomes 3, -1. And -2, 0 becomes 0, -2. So our points became 4, 2, 3, -1, and 0, -2. As a side note, if we were to graph the equation y equals x, you'll notice that each of our points, the original to its inverse, goes directly over and reflects across y equals x, and we'll talk about that in a little bit. If a relation is defined by an equation, interchanging the variables produce an equation of the inverse. So find the equation of the inverse relation, y is equal to x squared minus 5x. And that's simply what we're going to do. We're going to interchange everywhere I see a y, I'm going to put x, and everywhere I see an x, I'm going to put a y. A function is one-to-one if we have different inputs and have different outputs. That is, if we evaluate at a and b for our function and a and b are not equal to each other, then f of a and f of b should not be equal to each other. Or if a function is one-to-one, the outputs are the same, then the inputs are the same. So if what we have on the have as the result, we must have the same variable put in order to obtain that result. And let's see that in action. We read a function and its inverse of f with that -1 up top, and we read it as f inverse. A one-to-one function and its inverse is, if a function is one-to-one, then its inverse is also a function. The domain of a one-to-one function is the range of the inverse, and the range of a one-to-one function is the domain of the inverse. A function that is increasing over time or is decreasing is also one-to-one. And I have a little visual of the domain and the range based on which one it is. So given that a function is described by 2x minus 3, prove that it is one-to-one. That is, it has an inverse that is a function. On the first page, we said that if we evaluated at f of a and evaluated at f of b, and the result is equal to each other, then the pieces that we're evaluating for, a must equal b. So we should prove this with this function. To do that, I'm going to replace my a value where I see x, so 2a minus 3, and b, 2b minus 3. We just said then that our functions should be equal to each other. So I'm going to set f of a equal to f of b and simplify. And when I simplify, I should end up with a equals b. When I add 3 to both sides, I have 2a equals 2b. And when I divide by 2, I have a equals b. So since when I had f of a and f of b, I ended up with a simplified version of a equals b, this does tell us that f of x is one-to-one. Let's say that I have the function x squared. Prove that it is not one-to-one. So if we're going to show that it's not one-to-one, we have to provide an alternative answer or an answer that disproves our theory. So if I were to try the two values, x is 3 and x equals -3, and I evaluate, I put in two different values. However, I end up with the same answer. 3 squared is 9 and -3 squared is 9. We should have got two different answers. Similarly, we could also show that f of a has to equal f of b. Therefore, then a equals b. When I substitute in f of a, I have a squared. And when I substitute f of b, I have b squared. When I set these two functions equal to each other, and I take the square root of them, I'll end up with plus or minus a equal to plus or minus b. So we could have any combination. I could have a with -b or -a with +b, and those are not equal to each other. So therefore, we found a counterexample. We also proved it using our theory so that this is not one-to-one. So our g function, g of x, is not one-to-one. We also could utilize the horizontal line test because we utilize Desmos quite frequently. Very similar to the vertical line test, the horizontal line test will tell us if it's one-to-one. So when I'm looking at my first linear function here and I draw a horizontal line, I notice that it's only touching my graph one time. And since it's only crossing my graph one time, I can say that it is one-to-one. I also know that it's a function because it also passes the vertical line test. However, with part B, it is not one-to-one because when I do my horizontal line, it touches the graph in more than one place. Even though it is not one-to-one, we do know that it's still a function because it passes the vertical line test. So it can be a function and not one-to-one at the same time. Here I have a cube root function, and it does pass the horizontal line test, so it is one-to-one. And also a function because it passes the vertical line test. However, this next one, certainly not a function since it passes more than one time in many different locations. So this one is not one-to-one. But at the same time, because it does pass the vertical line test, it is a function. So how can we find the formula for an inverse? The function has to be one-to-one. It has to be one-to-one, so we have to check that first. So we have to use the first page using a formula option, or we can use the horizontal line test. If it is not one-to-one, we cannot find the inverse. So it has to be one-to-one, so verify that first. Then what we will do is replace f of x with y and swap out x and y to solve for y. And we'll see that in action. Our first example, I have determine whether the function is one-to-one, and if it is, find the inverse. I know that it is one-to-one because it passes the horizontal line test. So yes, it is. So we check it off. It is one-to-one. It passes the horizontal line test. Now we'll replace our f of x with y because f of x we know is just fancy wording for y. Y is equal to 2x minus 3. We'll interchange our x and our y values. X is equal to 2y minus 3. And then solve for y. I'll add 3 to both sides. And then divide by 2. So x plus 3 divided by 2 is our y value. Now substituting y back with our inverse, since now we found the inverse. So f inverse is x plus 3 over 2. Determine whether the function 2x over x minus 4 is 1-to-1. As I'm looking at our graph here, I do see that it passes the horizontal line test. We also could verify using functions, using our a and our b. I'll replace x with a. So is 2a over a minus 4, is that equal to 2b over b minus 4? I'm going to look at our greatest or least common denominator. And when I multiply by the least common denominator of a minus 4, b minus 4, and similarly here a minus 4, b minus 4, here our b minus 4s are eliminated and our a minus 4s are eliminated. That leaves us with 2a times b minus 4 equal to 2b times a minus 4. Multiplying across, I'll have 2ab minus 8a equal to 2ab minus 8b. Subtract 2ab. I now have negative 8a equal to negative 8b. Divide by negative 8, and I again have a equals b. So we verified algebraically as well. Currently, I have y is equal to 2x over x minus 4. I'll swap out my variables. So now I have x equals 2y over y minus 4. To start solving for y, I'm going to multiply both sides by y minus 4 so I can get rid of that denominator. These will be eliminated, and I'll now have x times y minus 4 equal to 2y. I will distribute, so I have xy minus 4x equals 2y. I'm going to get all my y's together, so I'm going to subtract xy. Now we have 4x equals 2y minus xy, and I can factor out my y value. Negative 4x equals y times 2 minus x. Divide by 2 minus x. And now we've gotten our y value by itself since these are eliminated. So our inverse function is negative 4x over 2 minus x. Let's take a look at x cubed plus 2. We'll solve and make sure that it is a one-to-one function algebraically. We know then by doing so that g of a has to equal g of b. So a cubed plus 2 has to equal b cubed plus 2. I subtract 2 and now I have a cubed equals b cubed. When I take the cube root, it doesn't matter if it's positive or negative, we'll still have a equals b. So it passes the horizontal line test, and we can also see that it's graphed here as well. We'll interchange our x and our y values. So x is equal to y cubed plus 2, and then solve for y. Subtracting 2, I have x minus 2 is y cubed. and then taking the cube root, I have the cube root of x minus 2. The inverse g function then is the cube root of x minus 2. And what I have here on the left is the graph. On this top one here is the original function, and this bottom one here is the inverse function. And here is that y equals x line again. So every point reflects across that line. I have the function 2x minus 3 and the supposed inverse section of x plus 3 using the same set of axes, and then compare the two graphs. So I just have some set of ordered pairs. My ordered pairs, when I substitute in -1, 0, 2, and 3, end up with -5, -3, 1, and 3 respectively. So when I graph these points, -1, -5, looks something like this. When I substitute values in for the inverse function, we'll notice that our x and our y values have simply interchanged themselves. But yet our graph is still going through y equals, or reflecting over y equals x. This will always happen with inverse functions of one another. Let's talk a little bit about the composition of functions and their inverses to prove that they are inverses of one another. We have to prove that both the composition of f inverse of the function and the function of the inverse are also, we have to prove both directions in order for us to ensure that they are inverses of each other. So both of these have to be proven. Both of them. So we'll start with f inverse of the function. So that means then wherever I see in my f inverse of f of x, I'm going to replace within my f inverse function, I'm going to replace it with my f function, f 5x plus 8. When I'm looking at my inverse function, then I'll have 5x plus 8 minus 8 over 5. Simplifying, my 8's disappear. So I'm left with 5x over 5, and we have x. So we've already proven the top one. Now we have to do f of the f inverse function. This time I'm going to plug the inverse function into my f function. So I want to take f of x minus 8 over 5. So wherever I see x in my f function, I'm going to replace it with x minus 8 over 5. So 5 times x minus 8 over 5 plus 8. Here I see my 5's will end up disappearing, and I have x minus 8 plus 8. These disappear, so I have x. So I have shown that through the composition of functions, these two functions are certainly inverses of one another. And this last one here, use compositions to show that they are inverses of each other. I'm going to start off with f of -1 of f of x. So wherever I see x in my inverse function, I'm going to put in x plus 5 over 3. So 3 times x plus 5 over 3. My 3's, minus 5 at the end for here. My 3's will disappear, and I'll have x plus 5 minus 5, which certainly equals x. Now I have to show f of the inverse function. So wherever I see x, I'm going to replace it with my inverse function, with my original function. So 3x minus 5 plus 5 all over 3. Our 5's will end up canceling, and I'll have 3x over 3, which certainly simplifies down to x. So the function and f of inverse are certainly inverses of one another based on composition. And this concludes our lesson on utilizing